Hello my dear friends, welcome to Canonical Vantage. If you're new to this channel, please hit that subscribe button and also hit that notification bell so that you won't miss any of my future videos. Now, what are we going to talk about in this video? We're going to deal with how functions are being represented on a paper or on your computer, because there must be a need to model the functions that we discussed in the previous video. The link is in the description if you missed that video. In the previous video, we introduced you into what is a function, and in this video we're going to talk about how functions are being represented, are being modeled on a paper, because there must be a need to represent these functions in a, or there must be a way we can write these functions on a paper, and that's what we are going to deal now in this video. Now, there are many ways in representing a functions, and in this video we're going to consider 5 ways of representing a function. The first one is the mapping diagram. Just like what you are seeing now on your screen is an example of a mapping diagram, where values in the domain are enclosed in one shape, and also the values in the range are also enclosed in a separate shape, and the values are connected through an arrow starting from one element in the domain pointing to another element in the range. Now, the second way of representing a function is through a table of values, where we see the x values written on the first row and the y values written on the second row. Now, you may see that a table is represented horizontally, but in fact you can also write or express or draw the table vertically. Whichever way you choose is up to you, so long as the convention followed in mathematics is that the first row represents your x values or your domain, and the second row represents the y values or your range. Now, how do we write them in horizontal way? Now, the first column should be your x values or your domain, and the second column should be your y values or your range. That's how we follow it as a convention in mathematics. Now, the third way of representing a function is through a collection of x and y values. We know from experience that a collection of x and y values is just the same as saying as a collection of ordered pairs. We know that an ordered pair is just a pair of x and y values, where the first number that appears is an x value and the second value that appears is the y value. Now, this collection of x and y values is enclosed inside a pair of curly braces. Now, the fourth way of representing a function is through a graph. We know from our previous experience that a graph is just a collection of dots connected together. Now, the fifth way of representing a function is through an equation. We've dealt with many kinds of equations before in our previous experience of mathematics. Now, not all equations that you see is automatically identified as a function. Now that we've learned the 5 ways of representing a function, it's now time to know things that we need to consider in identifying a function. Why? Because whenever you see a mapping diagram, you don't automatically and immediately identify it as a function. There's some rules considered. The same way, whenever you see a table of x and y values, you don't immediately identify it as a function. By the same way, whenever you see a graph of a certain equation, you don't automatically identify it as a function. And that's why we're going to move on to our virtual blackboard and see how do we identify functions. Welcome to our virtual blackboard. We now begin to learn how to identify a function out of a given relation. Because, like I've said, whenever you see a mapping diagram like this, you don't automatically identify such a relation as functions because there are rules to follow. Now, how do we know that a mapping diagram is a function? Very simple. All you need to remember is that each element in the domain must be mapped exactly once to any element in the range. So here we see 1 is mapped to 4, 2 is mapped to 5, 3 is mapped to 6, and now we know that each element in the domain is mapped exactly once. Okay, remember that. Remember that element in the domain is mapped exactly once. I can't stress that enough. Okay, it must be mapped exactly once. So in this case, since we see that each element in the domain is mapped exactly once to each element in the range, we say that this mapping diagram is a function. Okay, now let's move on to the next. This one, okay, this one here. Now, each element in the domain is mapped exactly once. You see that by looking at the line protruding or an arrow protruding out of 3. There's only one line protruding out of the number 3, and also 2, and also 8. You see that each of these elements in the domain is mapped exactly once, but only one element in the range. Now, you might think this must not be a function. No, you're wrong, because even though there's only one element in the range, this mapping is still a function. Why? Because you might think of a constant function. Whatever value you take out from a domain, it maps exactly to only one element in the range, and that is a constant function. Here, this is an example of a constant function displayed as a mapping diagram. Okay, so this is a function. Next is this mapping diagram here. This is exactly the opposite situation in the second example. So, in this example, we see that there is only one element in the domain and it is mapped to all of the elements in the range. Now, remember that an element in the domain must be mapped exactly once only. And we see that this -2, which is an element in the domain, is mapped how many times? 1, 2, 3, 4. You can see that by looking at the lines protruding out of number 2 or out of -2. You see 1, 2, 3, 4 lines, or you might think those are arrows, okay? The 4 arrows protruding out of negative 2, and that means the negative 2 is mapped 4 times. So this example is not a function. Okay. Now let's move on to our last example. Again, this is a relation, but now let's look at how many. I'm giving you a trick here. Just look at how many lines are protruding out of an element in the domain. Okay, this negative 8 has one line protruding out. 0 has one line protruding out. Negative 3 has one line protruding out. And sadly, the 4 has 2 lines protruding out of it. So this is a sign that this is not a function. Okay, so that's it. That's how easy it is to identify if a mapping diagram is a function. Now let's move on to our next part of identifying functions. Now, like I said, a function can also be represented as a table of values. And here you see two tables. One is displayed, the values are displayed vertically, and the other table where values are displayed horizontally. It doesn't matter whether the values are written vertically or horizontally. Now, let's try to observe the first table where the values are written vertically. We see that each element in the domain is mapped only once. Okay, you see negative 3 appears once in the list of domains or list of elements in the domains. Negative 1 also appears once, and so with 0, 2, and 5. So each element in the domain appears once, and that means an element in the domain is mapped exactly once to an element in the range. So this is a function. Now let's move on to our second table. So in this example, we just need first to look at the values or elements in the domain. We have negative 6, negative 4, 2, negative 4, and 7. We see that negative 4 appears twice. Now, since negative 4 appears twice in the domain, we now look at their corresponding element in the range. We see the first negative 4 is mapped to 0, and negative 4, the second negative 4 is mapped to 3. Now, if that is the case, then this tells us that this table or this relation is not a function. You need to remember that each element in the domain must be mapped exactly once. Okay, in this case, the negative 4 is mapped twice. The negative 4 is mapped to 0, and negative 4 is also mapped to 3. So, negative 4 is mapped or paired twice. So this is a sign that this is not a function. Now we move on to identifying functions. Now we move on to identifying a function out of a relation represented as a set of ordered pairs. Let's consider set A. Just observe if an element in the domain, okay, we see 1, 0, 2, and negative 3 as elements of our domain, and we have 2, negative 3, 6, and 4 as elements of our range in set A. Now ask yourself, is an element in the domain paired ones? Let's see. We see 1, we see 0, 2, and -3. And is mapped only once. So this tells us that this set of ordered pairs is, this must be a function. Now let's move on to set B. We have an ordered pair 0 and 1, an ordered pair -1 and 2, an ordered pair 6 and -3, an ordered pair 0 and 4. Let's identify the elements in the domain. We have 0, -1, 6, and another 0. Let's try to see whether the paired elements are the same. See, this is 1 and this is 4. So we say that this set is not a function. Again, we see that the element 0 is mapped twice or paired twice. A 0 is paired to 1, and the same 0 is mapped to 4. This tells us that this is not a function. Each element in the domain must be mapped only once, and here we see that 0 is mapped twice. So now let's move on to set C. We see an ordered pair A and K, B and C, Q and M, P and R. So all of the elements in the domain, the A, B, Q, and P, are unique. So therefore, this is a function. How about set D? Just need to see the elements in the domain. You see E, K, X, K, and E. We see that E appears twice and paired twice. We see that K appeared twice and also K is paired twice. Okay? Here we see E is paired to F and another E is paired to S. We see a K paired to N and another K is paired to A. So this tells us that this is not a function. So now we move on to identifying whether certain graphs are functions. Now, this is very interesting because you just need to use a tool called the VLT. The VLT stands for vertical line test. Okay? Vertical line test. So that's the meaning of VLT. Now, it's very easy. You just write a vertical line that will intersect or pass through the graph of a certain relation. And if that vertical line passes through the graph at exactly one point, that is a sign that a certain graph is a function. Now let's try this linear graph. We draw a vertical line anywhere along the graph. We'll see that this vertical line passes through the graph at exactly one point. Here, 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 here. Anywhere along the graph, the vertical line passes through that graph at exactly one point. So we say that this graph is a function. Let's move on to the next. We see this is a parabola, and let's try to write vertical lines that will pass through this graph. Draw a vertical line. Okay? Every time we draw a vertical line, the vertical line passes through the graph at exactly one point here, 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 and here. So we say that this graph is a function. How about this graph at the center? Okay, so let's see. We draw a vertical line. It does not pass through, and that's okay. We draw a vertical line here, and here, and here. And actually, this must be extending that way. Okay, so we see that the vertical line is passing through the graph at 2 points, here and here. And this line passes through the graph at 2 points, here and here. Also, this vertical line passes through the graph at 2 points. So, we say that this graph is not a function. Okay? Whenever the vertical line passes more than once in the graph, we say that that graph is not a function. Now, how about this one? We draw a vertical line here. It does not pass through the graph, and that's okay. We draw a vertical line here. It does not pass through the graph. That's again okay. But if we draw line here, or like sometimes we say that a vertical line is tangent to a graph. Remember that a tangent to a graph is a line that passes exactly once through a graph. Okay? So this line we call here is tangent to the graph. This line, the vertical line, is tangent to the graph because it intersects the graph at exactly one point. Okay? But if we draw another line, several vertical lines, we see that the vertical line passes through the graph at 2 points. Here, 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 and here, and here, and here. Okay? So the vertical line passes through the graph at 2 points, and the vertical line test fails. So the vertical line test fails in this graph, and so we say that this graph is not a function. Let's move on to our next graph. Okay? You just draw a vertical line anywhere along the graph and see the intersections. We see that the vertical line passes through the graph at exactly one point, and we say that this graph is a function. Okay, so that's it. Okay, I hope you enjoyed this video.